welcome back. Well, I hope you've gone and made your repeats. I've made mine. If you're sitting there having not actually gone and made your repeats, pause me now and go and do them. Okay? You have to actually carry this out to get a real sense of what this takes to make good data in science. So don't cheat, go and make your repeats. We'll all wait. Okay, glad you did. As you can see, I've got some variation in my repeats here. I've predictably measured exactly the same number for my height of my 5 lines. For my grass, because it was a more difficult thing to measure, because it wasn't perfectly straight, it was very, very light, and it doesn't have, a very, very distinct start and end point, because it's something from nature, which, we should get used to. Then I've got some variation here in my measurements. And for my time around the table, I have some quite significant variation. Now let's just have a little look at what I've done with that data. So the first measurement I made of myself walking around my table was 7.72 seconds. But then you can see in the 4 repetitions afterwards, I got a significantly shorter time. Now this can happen quite a lot when you make measurements, folks. You get better at taking the measurement. You get more certain about where to start and stop your measurement. You get better at carrying out your experiment. So that is why I said that 5 repetitions is your minimum number. Okay, there is nothing to say that you can't make more repetitions than that. And if through the course of repeating your measurement, you notice that certain results are out of bounds, that seem anomalous, then get rid of them. Okay, they do not have to be involved in your mean, and that is the entire point of repeating your measurements anyway, to get a set of measurements that you can be far more sure of that are reliable. So I am not going to include that 7.72 in my mean, and I would never have known that that is not really a realistic time for me doing this particular measurement if I hadn't made those repeats. So you can see I've got 6 repeats in total of that measurement, but I'm only going to include 5. Okay, I'm only going to include the ones that I feel are proper representations of what was going on there. So we're going to go ahead and calculate the means. See you in a moment. There we go. So this brings us to our first cardinal rule of processing data, folks. So processed data is when you've carried out any manipulation or calculation at all to your raw data. So these are all raw data. They have come straight from a measuring device without anything further done to them. You've literally just read them off a screen or read them off a scale and written them down. That is raw data. If you now do anything else with that data, that is data processing. And the first cardinal rule of data processing is your processed data cannot be more precise than your raw data. So any means that we calculate must be to exactly the same number of significant figures as your raw data. You cannot have a mean or average that is more precise. So if any of these came from when we put these through our calculator, and our calculator, when we divided the total by 5, gave us a number that had masses and masses of decimal points, we absolutely cannot write all of those down. And I don't think it's good practice to write down everything your calculator says and then have a final line rounding it, because none of those numbers are relevant or truthful when it comes to our data. So you have to be okay with rounding that answer off from your calculator screen and putting down a number that is the same precision as your data. Otherwise, it's just a lie. Okay, we absolutely cannot have a mean that is masses and masses of significant figures long. It is just not truthful. These aren't numbers, these are measurements. So now we have our 3 mean numbers. Okay, it's time to think about that final idea. We've done precision, we've done reliability. It's time to think about that dreaded word, accuracy. Now, I absolutely hate the word accurate. I find it incredibly unhelpful when used in reference to a physics experiment or any science experiment. Accurate means the right answer. So if your measurement is accurate, it means that is the actual length or time or volume or temperature of the thing you are measuring. But you will never know that. There is nothing that pops up from the universe to inform you, oh, well done, you've just made an accurate measurement. Okay? You cannot know that your measurement is accurate. You can know it's precise. You've used all the sig figs available to you from your measurement device. You can know it's reliable. You do the measurement 1,000 times and you keep getting pretty much the same number, but you still just don't know if it's accurate. So I really want you to try and not use that word. Now, I know as soon as I've said that, I'm going to use it throughout this series probably, just because I've said that. It'll come slipping out of my mouth without me even wanting it to. But try not to put it in official things like evaluation. So at the end of our experiment, we will be practicing an evaluation. And it's so important that you try not to use the word accurate. It very rarely gets you marks. People often use it as just a throwaway comment and it really doesn't mean anything. So I really don't like the word accurate at all and I want you to try not to use it. I mean, it's more than I don't like it. I know that it doesn't get you marks. However, the idea of accuracy, of a measurement being the correct measurement, is important to think about. Now, if we're ever sure of anything as experimental scientists, it is that our measurement is inaccurate. Okay, there has never been a perfectly correct measurement made in the history of science. Okay, we are always going to be getting some aspect of that measurement wrong. So instead of trying to describe verbally how accurate our measurement might be when we really don't know, what we do is state a range of numbers where our measurement is very, very likely to sit inside. We try and compensate for human error, for discrepancies in our measurement devices, for things that we can't necessarily account for, such as very light, oddly shaped things that we're trying to measure. We give these measurements uncertainty, a range of values in which our measurement is very, very likely to lie. So we are accepting and we are acknowledging to the rest of the scientific community, I know that my measurement is not perfect, but I am very sure that it lies inside this range. So that is what we're going to learn to do next, folks. We are going to put numerical uncertainties onto these measurements that we've taken now. And there are two major uncertainties that we cover in the higher course: reading uncertainties and random uncertainties. We're going to focus on reading uncertainties first, and I'll see you for that in the next video. Thanks, folks.